Till now, in our SSD1306 display series, we have done a hands-on practical using ESP-IDF platform, walked through a cross-platform universal library, and explored the datasheet in detail. In today's video, we are going to cover STM32 CubeIDE platform and draw our very first pixel on the display using our black pill board. And here's the exciting part. From the next video, we will step into the world of the LVGL graphics library. If you haven't watched the earlier parts of this series yet, you are missing half the fun. Go check them out first. Namaste and welcome back to Avinashee Tech. Here, we dive deep into embedded systems, decode data sheets, build real-world projects, and demystify microcontrollers and communication protocols. If embedded tech excites you as well, hit that subscribe button and join me on this journey. Let's switch over to the STM32 IDE and implement the same thing using our STM32 F411 chip. I already have a project created, so I will just go ahead and open the .ioc file. In the clock configuration tab, HSE is selected as the system clock source with a value of 25 MHz. In the pinout tab, under the timers section, we are using TIM2 to help us count microseconds. Prescaler is set to 24, so we get a 1 MHz timer or 1 microsecond per count. Under the connectivity section, we enable the SPI1 peripheral, set the mode to transmit only master, data size is set to 8-bit, and the baud rate prescaler is configured such that the SPI clock stays below 10 MHz. Obviously, you can always fine-tune the system clock for closer values. Clock polarity is 0, that is low initially, and phase is again 0, which means leading edge. In SPI.C, we define both the SPI peripheral pins and non-SPI GPIO control pins like CS, TC, and reset. Although MX SPI1 init function already configures SPI1 peripheral in the main source file, I have still added key members of the SPI handle structure here: mode master, data size 8-bit, clock polarity and phase, MSB first data order, and baud rate settings. HAL SPI init is then called to apply this configuration. In the SPI transfer function, it's just a single line: HAL SPI transmit along with the required arguments. HAL GPIO write pin is used to toggle the reset, CS, and DC pins between low and high levels as needed. In SSD1306.C, for microsecond level delays, in the delay US function, we reset TIM2's counter to 0 and spin in a loop until the required delay is achieved. In the OLED begin function, we call GPIO init to configure the non-SPI GPIOs using the GPIO init structure, set the mode to output, and apply the configuration with HAL GPIO init function call. In the main source file, we define the display width as 128, height as 64. Non-SPI GPIOs are initialized in MX GPIO init, SPI1 is initialized in MX SPI1 init, Timer 2 is initialized in MX Timer 2 init. The SPI pins are configured for alternate function mode in the HAL SPI MSP init function. In our main application, we start Timer 2 using HAL TIM base start to make our microsecond delays functional. Then we call OLED begin with width and height. The switch cap VCC macro is used for enabling the charge pump. Reset flag is also set to true. Next, we draw a single pixel at the same coordinates as before, x equal to 10 and y equal to 10 using OLED draw pixel. Then we call OLED display to push it to the screen. Let's build the code and flash it to our black pill using ST-Link v2 debugger. Once the flash is complete, let's check the screen. Yep, the dot is live. Let's take it one step further and redraw the letter H by lighting up the right pixels manually. Amazing. Let's quickly recap where we are in this series. We began by exploring the SSD1306 datasheet, then moved on to writing platform-independent C code to control the OLED display. Next, we customized that code library for the ESP32 using the ESP-IDF platform, adding SPI communication and specific utilities like delays. After flashing the code, the display worked just as expected. Then, we repeated the same process for the STM32 black pill board using STM32 CubeIDE, integrated the SPI functions, uploaded the code, and got identical results. So now we have a fully working SSD1306 OLED library running on both ESP32 and STM32 microcontrollers. In our upcoming videos, we will be taking things a step further. That is, discussing the LVGL graphics library and using it to display text, images, and eventually custom UI elements. If you found this helpful, don't forget to like the video, share it with others, and subscribe to Avinashee Tech for more deep dive embedded content. This is Avinashee Tech signing off.